Today we study X20, Newton's law of universal gravitation. Unlike many of fundamental constants, universal gravitational constant capital G has experimental uncertainty. And remember the unit. The gravitational potential can be directly derived from the gravitational potential energy. So we know how to compute the gravitational potential energy by making use of the gravitational integrating the gravitational force. And usually we take the reference value u goes to 0 as the distance goes to infinity. So if you consider the gravitational force between two massive objects, and if you want to replace this test mass with another, it is convenient to compute the gravitational potential that is independent of the test mass. So the gravitational potential is the same as gravitational potential energy, except that we divide this test mass away. The result is the gravitational potential in comparison with the gravitational potential energy. We use V instead of U. And you notice the mass of the test mass has been disappeared. So the denominator and coefficients are the same, but we have only the mass of the particle at the origin. We can see this function decreases arbitrarily small to the negative infinity as r goes to 0. And it approaches 0 and never pass through the x-axis, r-axis. Now, we want to compute, you remember, from the potential energy, we take the minus gradient to find the force. And this force can be expressed in terms of gravitational field or gravitational acceleration. Usually G is constant on the surface of the Earth, but in general it is not a constant. So just like what we have done with the gravitational potential energy in terms of potential times mass, so we divide this mass away, then it is G is a minus gradient of a potential instead of potential energy. That is mass times the potential. Now the coefficient minus the GMM can be pulled out, and we consider the minus gradient 1 over r. Minus gradient of potential, and potential is minus gm over r, so minus minus becomes plus 1 over r. Now we apply chain rule. First, take the derivative with respect to r, and then multiply the gradient of r. We remember that the gradient r is nothing but the unit radial vector, that is the position vector divided by its magnitude, and that is r. Therefore, it is minus x over r cubed. If we multiply the mass, test mass in here, you can reproduce the gravitational force between the capital M and small m. It follows the inverse square law, and it can also be written in the form ER hat divided by R squared, and negative sign in here indicates that the force is toward the center. So, okay. Find fourth statement regarding the parameterization of a spherical volume V of radius r centered at the origin. We use the spherical polar coordinates r, theta, and phi. Point X on the spherical surface, sphere, z-axis, we introduced angle theta, that is the polar angle, then unit radial vector, this is our ER hat, nothing but the ER hat, has the cosine, this z component is cosine, and perpendicular component on the xy plane, that is sine, this is cosine, and this is sine. And then we introduce the angle phi, azimuthal angle phi, measured from the x-axis counterclockwise. In that case, its x projection is a sine cosine phi, and y projection is sine theta sine phi. So this is the polar coordinate parameterization of the unit radial vector. We can see the polar angle theta begins with theta equals 0 when it is directed positive z-axis, and when we increase, this is the maximum value, it reaches pi, whose cosine value runs from +1 to -1. When you carry out an integral should be from 0 to pi, or d cosine theta, if I have this Jacobian. If I carry out the integral in terms of cosine theta, then it runs from -1 to +1. And the azimuthal angle runs from 0 to 2 pi. That's 2 pi. Number 3, parameterization of a spherical surface S of radius r centered at the origin. Look at this figure. Differential arc length on the circle of radius r in the interval theta plus from z-axis theta d theta, and this angle is theta plus the d theta. These arc lengths. This is the radius, so that is r d theta. Differential arc length on the circle of radius r sine theta. What is r sine theta? It's a projection, radius projection onto the xy plane. This is r, so this is r cosine, and this projection is r sine theta. This radius of r in the interval, azimuthal angle can be changed from phi, and this is d phi, and this angle is a phi plus d phi. So this is a radius, and this is the arc length, so r sine theta d phi is the arc length. This arc length r sine theta d phi. The differential area of the spherical surface in the region delta theta, d theta and d phi. Okay, this is a d phi angle, and this is a d theta angle. In that case, this part, this side is r d theta, and this side is nothing but r sine theta d phi. In the limit, as d theta and d phi goes to 0, this patch becomes flat, and it is a rectangle. And this area of the rectangle is r squared d phi and sine theta d theta, or d cosine theta. The sign difference, actually the sine theta d theta equals minus d cosine theta. The reason why I do not put the negative sign is I will replace the order of the lower limit and upper limit. I will exchange to absorb this negative sign inside the integral. So area element on the surface is parameterized in this way, or this can be expressed in terms of the cosine theta, and the cosine theta runs from -1 to 1. The infinitesimal surface element is parameterized by its radial direction. Number 4, the gravitational field G at point X due to a point mass M. This is what we have derived previously, and this is a unit radial vector. According to the divergence theorem, for any volume V whose closed boundary surface is S, so this is a volume, and we have a surface that surrounds the volume V, that we use this notation, boundary. This is not the derivative, this is the topological expression. The boundary of V is this closed surface. The divergence theorem, what we studied earlier, states that divergence of any vector field integrated over a volume is identical to the integral over the closed. This circle represents the closed surface surrounding the volume, and this volume integral is replaced with the surface integral as a scalar product with the original field. So we substitute this gravitational field into the right-hand side, and we know how to evaluate the surface integral over a sphere. And gravitational field scalar product surface, we remember that this is proportional to ER hat, and this surface element is also proportional to ER hat. The scalar product of ER dot ER, that is just number 1. So now we have just integral over the azimuthal angle from 0 to 2 pi, and polar angle from 0 to 2 pi, and this is the surface element multiplied by these differentials. And then we have over factor minus gmm, and we have the denominator in the integrand. This one appears. Now we evaluate this integral over a surface of a sphere of radius r. The numerator, denominator, r dependence cancels exactly. What we have is just angular integral, and this angle integral for the azimuthal angle is 2 pi, trivial integral, and the polar angle integral is expressed in terms of another trivial integral that gives number 2. 2 pi multiplied by 2 is 4 pi. That is the solid angle of the three-dimensional space. Therefore, the right-hand side of the surface integral coming from the divergence theorem gives minus 4 pi gm. The gravitational flux due to the point mass m at the origin, this one, is now evaluated to be minus 4 pi gm. Now we return to the volume integral. The surface integral can be done very easily, and we have found this value. But you remember, this one has divergence is always 0 if r is not equal to 0. However, at the origin, this field is divergent. Although it is very difficult to evaluate the left-hand side, what we have done by making use of divergence theorem gives a trivial integral that is minus 4 pi gm. Now we have arrived at a very important situation. The surface integral is identical to the volume integral of the divergence because of the divergence theorem. Now, let's see. This is a constant. Mass can be always expressed as an integral of a volume integral weighted by the density. Everybody knows that. So, this one can be expressed as 4 pi g density volume integral. Now, by making use of divergence theorem, this one is to be replaced with divergence g volume integral. Just erase this, forget about this, and connect these two. Then this integrand can be combined to give the integral to be exactly 0. This volume can be chosen arbitrarily. So why don't we take this volume to be very tiny one, such as V epsilon, and that is the circle of radius epsilon, and we take the limit as epsilon goes to 0. Goes to 0 means it is not exactly 0, but it is arbitrarily small. In that case, this, for a very tiny volume, this integrand is frozen to a constant value. So I can pull this integrand out of this integral as long as this volume is very, very small. Even though it is very, very small, it is non-zero. So I can divide this volume away. finally, I end up with this differential form of the Gauss law. Actually, this is called Gauss law, integral form of Gauss law that we use frequently in the next semester when we learn electrostatics. Hey, this one, finally, we end up with the differential form of the Gauss law. When we study electricity later, you will find that this electric field is just the charge density divided by permittivity constant for the vacuum. Find the false statement regarding Gauss law for a point mass at the origin. Point mass capital M is placed at the origin. This is what we have done already in the previous problem. All right. Point mass. Point mass means density of X is infinite at the origin. And density of mass is 0 if it is not at the origin. However, even though it is a because the mass divided by volume is defined by the density, mass is just a finite value. It doesn't decrease at all. However, volume can be chosen to be 0 if it is a point. That's the reason why this density is divergent as x goes to 0. However, it is not a serious catastrophic divergence because you still can integrate and we know exact value of the mass. This is a special case of Dirac delta function, and Dirac is with the Schrödinger Dirac established quantum mechanics, and Schrödinger is one of the person who established the quantum mechanics for non-relativistic particle, and Dirac is the person who installed the relativity in the quantum mechanics to describe the equation of motion, quantum mechanical equation of motion for electron. Anyway, he created, not mathematician, but physicist created very strange function that is in mathematics it is not a function because it is a strictly divergent, although nevertheless the integral is a trivial, just one. So I can replace this density, mass density divided by the mass of this point particle to be a Dirac delta function. You know, this is 1 over m rho volume integral. So rho over m is the delta function. Delta function, you don't be afraid. Delta function is any function whose volume integral is 1, and its integrand vanishes everywhere except at the origin. Now, we have reached the point, the divergence G was, you remember, divergence G is minus 4 pi G rho. And we remember, and rho is what? Rho is delta function. M, delta function. Just to replace mass times the Dirac delta function, substitute here to find the final result. And this is an example just of the electrostatic field that also satisfied the inverse scale law. And when you replace this overall coefficient minus Gm with the electric charge Q divided by 4 pi epsilon 0, what you obtain for the point charge at the origin, the electric field divergence is the same as the delta function, what you have done with the point mass at the origin for the gravitational case. In addition, any magnet consists of north pole and south pole. If you break a magnet, it becomes two magnets, and you can never separate the north pole from south pole. That's the reason why the magnetic charge is always dipole, and there is no fundamental magnetic monopole, unlike the electrostatic case, plus charge and minus charge. These two poles are separable. Because of that, this is an electric case. The charge density comes from the monopole distribution, either positive or negative charge. In the case of magnetic field, there is no north pole, south pole separated. So the sum of north and south, the contribution becomes always 0. So divergence B is always 0. You will learn in the next semester when you study the Maxwell's equation. Number 8, the gravitational potential energy for a system of particles can be constructed by making use of the gravitational potential energy of two-body system. If there were two bodies, the product of mass multiplied by the gravitational constant, put the negative sign on it, divided by the distance between the two particles. But what happens when we have three particles? Then there are three combinations. 1 and 2 share the gravitational force, 1 and 3, and 2 and 3. So this is the total potential energy of the system of three massive particles, and that can be straightforwardly generalized to the n-particle system. The two-body system can be studied. In the gravity, we have two massive particles that share the gravitational force. The two-body system can be easily described when we introduce the center of mass frame. The center of mass frame is the center of mass coordinate is just 0, the origin. So actually the center of mass coordinate is divided by m1 plus m2, that is 0. So we multiply the sum of the two masses. As a result, they have center of mass, Cm is here, m1, m2, and the distance from the Cm is opposite ratio, m2 and m1. And we define the relative coordinate vector that is not from the center of mass, but the difference of relative displacement of the two particles, x1 subtracted by x2. And we introduce the unit radial vector ER hat that is parallel to the relative coordinate vector, and R is just the distance between the two particles. R is not the distance from the center of mass to a particle, but the distance between the two particles. You have to remember. And then this unit radial vector can be expressed in terms of Cartesian coordinates with cosine and sine. And when it rotates at the CM frame, this makes a small circle, and lighter one makes a bigger circle. And the radial direction has a tangential direction, that is sine cosine flipped, and the sine is different for the derivative of cosine. Using these coordinates, relative coordinate r, we can express the position vector of x1 and position vector of x2 in terms of this relative coordinates. And the overall vector is nothing but the opposite mass ratio in units of total mass. You remember E1, E2, E3, they make a cyclic triad, so that is one. Just like that, radial, tangential, and third component that also satisfy the same relation. This relation is very useful to simplify down the following computation. The velocity of the relative coordinate vector r is just the time derivative of difference of the position vectors. We remember this is r and er. We take the derivative, then derivative of radius and derivative of unit radial vector. We remember derivative of unit radial vector is theta dot e theta. And because er and e theta are perpendicular to each other, we can choose this one and this one, that they are orthogonal. The square of this vector is r dot squared er squared plus 2 times r dot r theta dot er dot e theta, and r theta dot squared e theta squared. And because they are perpendicular, this one disappears, and radial velocity squared plus radius squared times angular velocity squared. Now we apply this one to the actual gravitational problem. The potential energy of the two-body system is given by, you remember r is the distance between the two particles, so that's quite good. Our representation in terms of relative coordinate is identical to this r. And factor k is a product of the gravitational constant and product of mass. Relative coordinate is given like that. We remember two-body system. In two-body system, we have frequently seen the reduced mass, that is the product divided by the sum of the two masses. Total kinetic energy of the system is sum of the kinetic energies, because and we have derived this one is identical to the 1/2 reduced mass, and this is the r vector dot squared. We just have derived. Okay. And the total angular momentum is r cross p, sum of the two particles. If we substitute this is x1 and this is x2. And mass m1 times velocity of the first particle, velocity. This derivative is the same factor appears, and this one is identical to this. Again, the second particle has the relation. Sure, there is negative sign on it, now minus the square becomes a plus. It looks complicated, but we have a denominator that has the square of the sum, and we have m2 squared m1, m1 squared m2. This is a factorized. It is m1, m2 multiplied by m1 plus m2. And this cancels the single power. Finally, we end up with the reduced mass multiplied by r squared, that is the relative coordinate squared, multiplied by theta dot. You remember, this is the orbital angular momentum of the whole system, complete system. That is, for a single particle, radius r and m, level r, then moment of inertia is mr squared, and angular momentum is I times omega, you remember. In the case of two-body system, m is replaced with the reduced mass mu, that is defined in here. R is the relative coordinate, just the distance between the two particles, r, and theta dot. So this orbital angular momentum is conserved. The reason is that the gravitational force is central force. Central force means the force is along the direction parallel to the relative displacement of the two particles that we call central force. As long as the force is central, the angular momentum is preserved. That is a constant of motion. Now, from this expression, why don't we square this? So angular momentum squared divided by mu r squared theta dot squared. So L squared over mu r squared and r squared theta dot squared. This is the one. Okay. Because this is identical to this, and angular momentum is a constant of motion. Constant of motion. So total mechanical energy is kinetic energy. What is the kinetic energy? This is the kinetic energy. And the potential energy. This is the potential energy. Kinetic energy is divided into two pieces. Radial component squared and angular component squared. Mu, what is that? R squared theta dot squared. R squared theta dot squared. This one. Plus potential energy. This angular contribution, rotational kinetic energy, this rotational kinetic energy can be expressed. This R squared theta dot squared, this one can be replaced with L squared over mu R squared. L squared over mu R squared. So 1/2 is here. So this part can be moved to this expression. So we define effective potential energy of the two-body system. The reason is that this orbital angular momentum square is a constant of motion, and it does not have any time derivative. It is a single function of r. You remember the conservative force and the reason for the angular momentum conservation. Okay, consider a system of two bodies. This is what we have done already. Total mechanical energy E and the orbital angular momentum L are both conserved. That's right. Axis of rotation is fixed because of the angular momentum conservation. Because the orbital angular momentum is conserved, this one is conserved. That is what we have already used to derive the effective potential. Let us look into the effective potential more closely. Potential energy is decreasing to the minus infinity. U of R is a minus. This K is a positive definite. However, we have positive sign and 1 over R squared. This is a much larger value as R goes to infinity. R goes to 0. So even though it is going down and for a relatively large R, as it approaches 0, it suddenly rises up and goes to plus infinity if we consider the effective potential energy. That is strictly different from the potential energy. The additional piece comes from the conservation of angular momentum, and this is actually the kinetic energy for the rotational kinetic energy. So anyway, we can reduce this problem into a one-dimensional problem with the potential, this effective potential. In that case, we are interested in the value of radius at which it does not feel any force. That means it's a derivative of effective potential becomes 0. So perhaps because of this structure of effective potential, when the energy is below this effective potential, then it is forbidden classically. When the energy increases to touches the minimum point of the effective potential, because this is a radius, it represents the uniform circular motion. Radius is completely fixed in that case. So circle. And if we increase the energy a little bit more, what we find is there are two turning points. It is forbidden going up because in that case, the kinetic energy becomes negative. It is classically forbidden. That means we can find the radius is somewhere between these two. We call this R max and R min. And actually, nobody knew that, including Newton, but Kepler found that the orbit, not using these formulas, but by analyzing the data collected by Tycho Brahe, Kepler found the orbit of planets are just ellipse. This elliptic orbit was found by Kepler by analysis, and Kepler was not the person who observed. The person who observed with his own bare eye without any telescope, who was Tycho Brahe. And the point at which it makes a circular motion is called alpha. And this alpha is called the semi-lattice rectum, alpha. And this alpha can be obtained by taking the first order derivative and put the value to be 0. Then solution is exactly the alpha, that is orbital angular momentum squared divided by mass, that's reduced mass, and k is gm1 and m2. All right, we repeat this one. We have found that this stable point, the equilibrium point is the radius of the circular orbit that is completely determined by the orbital angular momentum, and it is called the semi-lattice rectum. The energy is then fixed at the value of r equals alpha. Then it becomes orbit is a circular. And just like what I have just shown, it oscillates R max and R mean, and Kepler found that the orbit is ellipse. In addition, if we increase the energy further, then just touch the R axis in here, it becomes parabola. And if you add additional energy, then the orbit becomes hyperbolic. This hyperbolic orbit doesn't return to the same point again. It never returns. So this is a free orbit. It is not, it is just like it goes away and never returns. And this, for example, this is Earth, and we have moon. We want to search for moon, or we want to escape from the Earth orbit. In that case, the minimum energy required is a parabolic orbit. If I want to study the outside of solar system, I need a parabolic orbit not for the Earth, but for the sun. After escaping from the Earth, it is still trapped by sun's gravitational force. To escape from the sun, to go away of the solar system, then we need an energy relative to the sun that is a parabolic orbit. And if we have large enough energy, we can follow the hyperbolic orbit and it will never return. All of this was found by based on the observation of Kepler's elliptic orbit. Now we consider the solutions, two solutions. This is we expect that it is coming from the quadratic equation, usually have different two solutions. And in special case, we have the double root. This is how to find it. The conservation of energy and conservation of orbital angular momentum requires this. And substituting r dot equals 0, r dot equals 0 means orbit the radius, actually two-body system. This radius sometimes increases and then stops, decreases and then stops. So we want to find the condition for the r dot equals 0, r dot equals 0. In that case, we have r squared. It is a quadratic equation with respect to r. So middle school student can solve this quadratic equation, and value of r is determined by this discriminant. When the discriminant becomes 0, it has a double root. When it has double root, the solution for the radius is just the semi-lattice rectum that is a circular orbit. The answer is this. Expressed in terms of k and alpha, the energy is completely determined like that. And the solution for the radius is the semi-lattice rectum, just I told you. And using this, you can find the potential energy and kinetic energy and total mechanical energy. They are all scaled by k over alpha, k over alpha, k over alpha. They're identical except that it is multiplied -1, multiplied by 1/2, multiplied by -1/2. This is a very interesting result, which is called the special case of the Radial theorem.